Hi, my name is Sam Lensgraf, and I'm a PhD student at the Dartmouth Reality and Robotics Lab. And today I'll be talking about Droplet, which is, to our knowledge, the first autonomous underwater assembly system for modular structures featuring a free-floating robot. Droplet is a solid first step towards more general autonomous underwater construction and assembly technologies. Systems like Droplet could enable cost-effective temporary coastal protection infrastructure. For example, a fleet of robots like Droplet could build a temporary breakwater in response to a predicted extreme weather event, and then disassemble that breakwater after the weather event. There are several unique challenges in the underwater domain that make reliably assembling structures difficult. Poor visibility makes vision-based global localization challenging, communication is limited, and currents make it hard for a robot to hold its position accurately. Droplet's key design feature that allows it to overcome these challenges is its use of passive error-correcting blocks. The error-correcting geometries on these blocks allow them to correct for large amounts of pre-drop and pre-grasp position error. You can see the example of passive error-correcting geometries in action to the right. We exploited passive error-correcting geometries to limit Droplet's dependence on sophisticated sensing, which makes it more robust when sensing is unreliable. We also make use of an opportune dropping strategy, where Droplet rapidly releases a block when it deems that there is a high likelihood of success. This allows it to robustly assemble blocks despite position noise. An opportune drop is triggered when Droplet receives two sensor readings within a tolerance region specified as a box around in configuration space, shown in gray, around the ideal drop location, shown in green. The block will properly align with the slot if Droplet's true position is within the slot's acceptance area, shown in cyan. The reliability of the opportune dropping strategy is limited by the probability that Droplet will trigger drop behavior whenever it's outside of the acceptance area. By changing the size of the acceptance area and the tolerance region, we can change how likely this event is and adapt Droplet to different sensing qualities. For example, different visibility conditions. We computed this probability for an idealized 2D scenario, and we show the results of that computation in the plot B on the right for increasing cone size in our passive error correcting features. A plot like this can be used as a design aid to adapt the system to different covariances of noise rigorously. We conducted an extensive experimental analysis of Droplet's performance. The key feature of our analysis was a set of full system trials in which Droplet built 3 different types of structures. The limiting factor for the size of the structures that Droplet was able to build was actually our ability to fabricate these blocks. So to overcome that, we conducted a large repeatability test in which Droplet picked up and placed a block 100 times. And it actually was able to do this successfully 100% of the time for all 100 of these trials. In the future, we'd like to extend Droplet to build with more realistic building materials. So right now we're working on prototyping cement blocks. And these cement blocks weigh about as much as Droplet itself. So we're looking into active buoyancy strategies to adapt Droplet automatically to the buoyancy of these blocks. And we're also interested in doing more rigorous field trials so that we can validate how well Droplet performs whenever it's actually being acted on by ocean and unpredictable types of currents. I'd be really excited to discuss this work with anyone who's interested in marine manipulation, collective robotic construction, on-land construction, or really anything like that. And I'd be really happy to work with anyone who is interested in replicating part of Droplet for themselves. So please shoot me an email or come find me at the conference, and I really look forward to meeting you. Thank you.